gamma spectroscopy, and I'm Anya Tomkovich.
I'm Gwendolyn Mark.
I'm Alex Rawle.
I'm Calvin Ayala.
Okay. So our objective of the experiment was to find the unknown amount of pre-1982 copper-rich and post-1982 copper-deficient pennies in a roll of 50 pennies using gamma spectroscopy.
So I'm going to explain a little bit of the physics behind what we did. So as Gwendolyn explained, we were trying to distinguish how many pre-1982 pennies we had and how many post-1982 pennies we had in a roll of unknown amounts of pennies. And as she said, the pre-1982 pennies have much more copper, so that's what we measured basically. And so the two most common isotopes found in pennies of copper are copper-63 and copper-65. And prior to our experiment, we exposed these to a neutron source. And some of the isotopes in the pennies underwent neutron capture, and so they became unstable copper isotopes. The isotopes copper-64 and copper-66. And basically what we did was we measured the decay of the copper-64 nuclei that underwent neutron capture because it's the more abundant isotope of copper of these two found in pennies. And so when the copper-64 decays, it releases gamma radiation. So when the nucleons basically drop to a more stable energy level. Specifically, copper-64 releases 511 kiloelectron volts when it undergoes electron capture to come to a more stable energy state. And right here you can see copper-64, and when it undergoes electron capture to come to a more stable state, it releases 511 kiloelectron volts and becomes nickel.
All right, so now I'm going to show you a bit of the equipment that we're working with here. So this and all does basically just what she just described. So I'll just go through and show you what each piece of equipment does real quick. This right here is basically the power supply and the analog to digital converter. So basically when you turn this on, it's as simple as just redirecting power to this machine, which we use in order to get the copper pennies to emit the gamma rays that we need to detect. So that's the high purity germanium detector, which is lined with lead, which is also lined with copper. And that's just so the gamma rays don't get in and don't get out. So we don't have outside sources of gamma rays that could conflict with the results in our experiment. So what happens here is whenever a gamma ray hits the machine, it sends a signal through a wire into this machine, which is back to that analog to digital converter, which basically transports that signal into something readable by the computer, so that we can look at a graph and be able to test the data in order to find out what the material or at least the energy emitted from the gamma rays is of the material in the spectroscopy. And they need liquid nitrogen cooling in order for this to operate. So yeah, I think it's pretty cool.
Alright, so this was the very first thing we did during the experiment. Well, at the beginning of the experiment. We had to calibrate the system, which was really, really, really hard to get. Really hard. Really hard. Really hard. So, what we did was open the system called JINA-CEE like the other group did, and we basically waited for our facilitator to put in a cobalt source in the germanium detector, the big red thing my friend showed me. All right? Stay with me. Stay with me. I know it's a lot. So then we just click the start button, and then we let it run for long enough to get this. And we compare that to a catalog of similar readings that previous scientists did. And if it was off, we would have to calibrate it. And that's where that came from. And then after that was calibrated, we got to read other materials. And we focused on pennies. We focused on reading post-1982 pennies, pennies made after 1982, pre-1982 pennies, pennies made before 1982, and a 50-50 mix, like halvesies. Yes. So we were trying to find the different isotope mixtures within these pennies because we know that America and the economic branch wanted to switch the materials because copper was a lot of money to make pennies. Yeah.
And parents, there's your proof that we were actually working here. I swear to God, you did not just pose for that picture. You did it, I swear.
Okay, so for the data collection, this is all the pre-1982 pennies, and this is the copper spike. So you can see that pretty much they were all copper, and that's just some extra stuff. And for the next one is, flip the button.
Take a quick button.
Oh, there it is, never mind. So the pre-1982 pennies, it probably looks the same.
No, it's,
Is it different? Okay.
Yes.
Oh, it's a little bit.
There's less copper
Wait, someone's in the way. Wait, which one?
Okay, and then the 0%, that's the copper reading. There's virtually no copper except for the plating. And that's, I think that was supposed to be post, but we put pre after 1982.
Yeah, sorry, this is the post.
No, that's right, it's a 0%.
Yeah, 0%, yeah, actually 0%.
Oh.
Sorry.
I messed
You got
that
it.
And one last one. The unknown, we found about a 50-50 mix.
Yeah, it was very close to 50-50, but we later did analysis, so that's
Yeah.
our next slide. So our results and conclusions. Right here in this table, you can see the peak area counts of each of those peaks of copper, 64. So, and the 0% pre-82 pennies, so all the new pennies we have a very low count of copper, and the 50% a little bit more, about 4,000. 100% has very high reading, about 7,300. And so, yeah, we saw that this was a very close to a linear relationship. So we were able to find. Right here is the peak area, and on the y-axis is the percent of pre-82 pennies. So you can see it's very close to a linear relationship. And so we found a trend line of the data, and if you click once more, and so you can see our results. So basically, we plugged in the peak area count of our unknown value, which was about 3,554 counts. And so we plugged it into the X value here, and we got 22 pre-82 pennies, so that's about 45% pre-82 pennies, and 28 post-82. That was our result according to our calculations. However, the actual result was 19 pre-82 pennies and 31 post-82 pennies. So we were a little bit off, and that can probably be attributed to the way in which we collected the peak area counts, which was a very rough way of kind of eyeballing where the peak began and where it ended. So that may be attributed basically to our error. And we concluded that gamma spectroscopy is a really good and minimally invasive way to find the concentrations of different isotopes, metals, in different types of alloys. So that's what we got.
Yeah.